Okay, so hello, welcome to my channel. Today would be a brief introduction to quantum mechanics. This is a very fun subject for me. So first of all, let's define what quantum mechanics is. Well, this is a field of study that is gonna tackle those like minuscule objects. For example, like particles, molecules, etc., etc. Well, to start off, we're gonna see a comparison between the quantum world and the classical world. The first we have to address is the physical behavior. In classical mechanics, a thing is gonna behave exactly how you expect it to behave. You can say it is predictable or deterministic. For example, you have a ball, you roll it. You almost certainly know how it is gonna behave. You're gonna know its position, its momentum, its energy, all kinds of stuff. But in the quantum world, things behaves a little bit differently. And this is where a lot of people find it confusing. So for example, you send in a particle somewhere, what you're gonna get back is a wave. Well, that's weird. A probability wave, to be exact. Well, I think that makes a little bit more sense. The wave is not the particle itself, but it represents the probability of you finding the particle there. So, for example, you have a wave like this, a very simple looking wave. This is probabilistic. So the probability of you finding the particle here would be very, very low, while the probability of you finding the particle here is big, and this is probably where it is. So you just do this. And next, we're gonna talk about the definition of this weird word right here, quantization. What is it? Well, quantization, I'll give you an example. Well, say in the classical world, you have the the energy of an object in the classical world. When you act on it with a force and you increase that force gradually, the energy of the thing is gonna increase gradually as well. So this is a graph right here. Alright, so as you increase the force that you act on the object with, the energy is gonna increase gradually as well. So this is like a frictionless environment. It's gonna be a very nice slope here. It's the energy and the force. Not gonna write it, but here it is. But in the quantum world, as you can predict, it's not gonna be as easy. So, for example, you have a particle and you shine a light and you change the frequency of the light gradually. How would you think the energy of the particle would change? Well, you would certainly think that it would change gradually as well, right? Just like in classical mechanics. But no, that is not the case. somehow. Yeah, I know it's weird. So what would actually happen here is, for example, you have your particle is here to start off the ground state. You shine a light and you change the frequency or the wavelength gradually. Well, at first, nothing's gonna change. It's just gonna stay here. But as you increase or decrease it, it is gonna have, like to a point, it is gonna have a jump. So it's gonna be here. You increase, you change the frequency gradually. And at one point, it's gonna make a jump to here. It's jump right here. And you do that, it's just gonna jump. And this jumping is called quantization. You have successfully quantized your energy. It basically means that like this is gonna jump instead of increasing gradually. So it's gonna behave like this in the quantum world. The energy is quantized now. So quantization basically means that your energy graph is just gonna look like a stair. It's gonna jump up, and decrease down. And you're gonna see this in a lot of quantum mechanics phenomena, like spin, angular momentum, and energy states. And we'll talk about those later. Today I'm just gonna do it very quickly. Next is operators. So what are operators? Well, let's start from the classical world first. In classical mechanics, they would certainly provide you with x value, p value, e, all sorts of stuff, and most of the time it would just be a number. Maybe they might include some variables, but those are still numbers. So in the classical world, you would have like x and p, but when you jump to the quantum world, this x would become x hat, and p would become p hat. So these are called operators. They don't give you the value. These guys have to act on something, and this something is a wave function, as we mentioned before. And they're gonna let you know roughly where it is. It's called an expectation value. So you can think of these like pure data, while these guys are like a computation that give you the data. Sorts of like that. And commutation, these values, they are commutative. And what does that mean? So for example, you have x times p. In the classical world, this would equal to p times x, because you just change the order. Nothing happens. But in the quantum world, when you change the order of these operators, things would change. So x hat, p hat is not equal to p hat, x hat. So we say that this is non-commutative because the commutation of x and p is equal to 0, while this is not. This basically means xp minus px. That makes it a lot easier. So we're done with that. Let's move on to the mathematical framework. First, of classical mechanics, the mathematical framework of it is mostly consists of differential equations. So you have to deal with a lot of calculus, a lot of changes, slopes, all kinds of stuff. But with quantum mechanics, you only deal with mainly linear algebra. So we say that quantum mechanics is linear. So they have the property called linearity, which means that just like vectors, a solution when you time it with a scalar is still gonna be a solution. So that's why I say that quantum mechanics is pretty much easier to understand than advanced classical mechanics. And next, the state of the system. The state of classical mechanics most of the time would be like a definite point in space that you know the x and p and like e of. Just like I said in the physical behavior, it is deterministic. You know everything about it. You just have to do the calculation. But with quantum mechanics, it's a probability wave. So this is very hard to determine exactly where it is. You're only gonna get a wave that you don't know the x, you don't know the p, you don't know the e of. You have to do like all sorts of stuff just to get a rough shape of the wave, to make out the rough position or momentum of it. So that would be it, I guess. Goodbye.